price of $200 per unit. If the total production cost in dollars for X units is given by C of X here, how many units of panel cell must be manufactured to maximize the profit? Okay, so that's what we're trying to do, maximize the profit. So let's first define what the profit is. Simple equation for profit is the revenue, which is the amount of money you generate by selling something, minus the cost, which is how much it costs you to sell that something. So, to figure out the revenue, when you're just selling some product, simple equation of that would just be the price per unit, how much you're charging for each thing, times the number of units sold. So you take how much you're charging times how many are sold, that'll tell you how much revenue or money is generated by selling. So, since we're trying to maximize the profit, that's going to be our main equation. So P would equal, well, it would be the revenue minus the cost. So the revenue in this case is the price per unit says $200 per unit times the number of units. It says we've got X units, so it would be times X. So since it costs $200 per unit, you multiply by how many units were sold to give you the revenue minus. They give you the cost function here, C of X. Just make sure you put it in parentheses. So you're subtracting the whole thing, so 500,000 plus 80x plus 0.003x squared. So this is already in terms of one variable, so we don't need a second equation in this case. So it'd be 200x. We distribute out that negative, it's negative 500,000. And then minus 80x. Minus 0.003 x squared. And then if we combine our like terms before we take the derivative, make it a little bit simpler. We have 200x minus 80x is 120x minus 500,000 minus 0.003 x squared. And now this is what we're trying to maximize. So now let's take the derivative, p prime of x. Derivative of 120x is 120. The derivative of negative 500,000 is 0, it's a constant. And we use the power on this one, 2 times 0.003 would be 0.006 x. And you set that equal to 0. And then if you just add over the 0.006x, then you can divide by 0.006. And you get x equals, well, to make this simpler, to divide without needing to use a calculator, just think, well, to get rid of that decimal, you'd have to move the decimal 3 places, right? Which essentially means you have to multiply by 1,000. That means you multiply the numerator by 1,000 as well. Oops, too many zeros there. So that would be the same as 120,000 over 6, which would just be 20,000. So that we can draw our number line now. We test the common sense interval here. Well, x is the number of units, so you can't sell negative number of units. Now, you actually, in this case, it would actually be 0 with a bracket because you could sell nothing. 0 units, that would make sense. It's not going to maximize the profit, but it's a reasonable answer that nothing's sold. And there's no upper limit, though, that we know of. So then p prime of x, we know at 20,000, derivative is 0. And here we could actually test 0 because it's not a critical number. So if you test 0 on the derivative, that gives you just 120 minus 0 is positive. And then over here, if you test something huge like 1 billion for x, then you can see that's going to make it negative. So this shows us the profit, p of x, would be increasing and then decreasing. So you can see the maximum would in fact have to be at 20,000 units. But for part A, our answer, 20,000 units. And then for part B, it says what is the maximum profit? So now we have to plug that back from the original equation. So that was P of 20,000. Well, that would be 200 times 20,000. Sorry, not 200, 120. Let's look at the simplified form right here. 120 times 20,000 minus 500,000 minus 0.003 20,000 squared. So let's see if we can figure this out without use our calculator again. With a profit of 20,000 units. Well, 2 times 12 is just 24, and then you just add on 1, 2, 3, 4, 5 zeros. Okay, now here's probably helpful to do is you're adding a comma, so that's 2,400,000. Minus, we add the comma here, that's 500,000. And minus 0.003. Then if you square 20,000, 2 squared is 4, and then you'd have 8 zeros. All right, lots of zeros. Okay, so we keep working this out. 2,400,000 minus 500,000, that's 1,900,000. And then here, to make this one easier to solve, just think, well, if this was 3 rather than 0.003, that'd be easier. So if you move the decimal 1, 2, 3 places, that's like multiplying by 1,000, which would knock off 3 of the zeros. So then you just have 3 times 4, 12, and we've got 1, 2, 3, 4, 5 zeros left. So that's 1,200,000. So that gives you 700,000. And the units here, it says, are dollars. All right, let's take a look at another example. Let's look at a geometric example now. So the rectangle has its 2 lower corners on the x-axis and its 2 upper corners on the curve y equals 9 minus x squared. So y equals 9 minus x squared, that's a problem. The 9 shifts it up 9 units. And the negative makes it up and down. You can see the x-intercepts here. What would make y 0 would be if x was 3 or negative 3. Oops. Go ahead and graph our problem. It goes through those. All right. That's not as symmetrical as it actually is. Let me try and draw that second part a little bit better. There. And it says we've got a rectangle, has its 2 lower corners on the x-axis, has 2 upper corners on the curve y equals 9 minus x squared. So the 2 lower corners are here, the 2 upper corners on the curve. So there's a bunch of different rectangles you can get like that. What we're trying to look for is the one, we're also trying to know what are the dimensions of the one with the largest area. Largest meaning maximum area. Okay. So let's go ahead and draw somewhere in here, draw a rectangle. I'm just going to put it right at -2 and 2. Put anywhere in there. So that's one of those rectangles we could get. There's 2 lower corners on the x-axis and 2 upper corners are on the curve. So our main equation, we want the one with the largest area, so we're trying to maximize the area. So area is going to be our main equation here. But we need to assign some variables. And when it's on an x and y axis like this, they're kind of essentially almost assigned for you already. So let's say this is some point, no matter where you draw a rectangle, this is just some point x, y. And you can see the height of the rectangle from there to there, that just represents the y coordinate. So I do y. And from there to there, that would be the x coordinate. And since we're going twice as long, that would be x there as well. So you can see the area of the entire rectangle would be 2x times y. That's what we want to maximize, so that's going to be our main equation. We want to take the derivative. However, what's in terms of two variables? Here to get in terms of one, notice we've already got y equals 9 minus x squared. We can substitute that in right there for y. So now we'll get the area just as a function of x. It'll be 2x times y 9 minus x squared. Then if you distribute out to 2x, the area is 18x minus 2x cubed. And then take the derivative of that. The 18 minus 6x squared. Set that equal to 0. Factor out the 6. You're left with 3 minus x squared. So if you set that equal to 0, you add over the x squared, you get x equals plus or minus the square root of 3. Well, let's think about our common sense interval in this problem. Well, x can't be negative, can't be 0, otherwise you wouldn't have a rectangle there, so it has to be something positive. But in this case, there actually is an upper limit on what x could be. Notice, because the biggest x could be here is 3. It can't actually be 3, otherwise you'd have a flat rectangle. So it'd be 3 with a parenthesis. So it has to be somewhere between 0 and 3. Positive square root of 3 is between that, but negative square root of 3 is not. So the only answer that makes sense is positive root of 3. When we test this on the number line, 8 times x, that would be 0 there. Here we could test 0 because it's not a critical number. 0 would make the derivative positive. Let's get up with 18. Here you could test square root of 3 is like 1.7 roughly, so this, you could test 2 here. If you test 2, let's see 2, 3 minus 2 squared minus 4, that would be negative. So this shows us the area, A of x, of that rectangle, would be increasing at the dot square root of 3 and then decreasing afterwards. So that would in fact be where the maximum occurs at root 3. But as for the dimensions, okay, so the dimensions of a rectangle are just the length and the width. So the dimensions just refer to the things that build up to it in the equation here. So, you know, x is root 3. So this side, since this is root 3, and this is root 3, as one of the dimensions would be root 3 plus root 3, 2 root 3. And then the other one we need to get what y is. So to get what y is, you just go back to this equation. Y would be 9 minus square root of 3 squared. Square root of 3 squared is just 3, so you get 6. So y equals 6, so you'd have 2 root 3 units, which units because it's on the x and y axis, by 6 units. Those would be the dimensions.